talking about convolutional neural nets, and I'm going to talk a little bit about Flax NNX, which we're going to be using for some of our homeworks. So we're in a really good place now. We talked about neural nets and how we can use gradient descent, and in particular, this phrase that's very hot is the idea of deep learning. And with deep learning, it's layer after layer after layer. And so to do the gradient descent, we're going to use the chain rule. And that's going to allow us to keep finding the gradient on our way back from the output back towards the input. And so that's what we talked about last time. So we have this great idea of linear combinations. We have activation functions. We can mix those together. We can do classification. We can do regression with it. If we're doing classification, we'll tend to use softmax and cross entropy loss. And if we're doing regression, we'll tend to use mean squared error loss. But these same ideas work in both cases. Back propagation works the same. It's just a different beginning of the loss idea. So we're going to be doing this learning. And so when you put data in, it flows through the network and you get some prediction out. And then if you have labels, you can use those labels to then do back propagation to compute the gradients. And then we use gradient descent to update the weights and the biases in those networks. So we're in a really great place. We do everything with matrix operations because they're very fast, especially if you have a nice GPU, right? Everyone has spent a bunch of money on all their NVIDIA hardware. We have a bunch at Georgia Tech. So, there's now a GPU makerspace where you can use your time and build models. So there are a bunch of GPUs on campus that you can use if the one on your laptop is not very good. Questions so far on where we are? We've made a lot of progress. We're covering a lot of ground at this point. One of the problems that we're going to bump into is the idea that modern data is actually really big. So the MNIST example that we're using in our first homework is really nice because it's black and white, and it's 28 by 28. So the input is just 784 numbers. It's great. Now, if we work with real modern information, modern images, modern video, you're talking about a lot bigger data. So we talk about a 1080p image, right? That's 1,920 pixels by 1,080 pixels. And then there's three colors, R, G, and B. So the numbers coming in are more like 6 million different numbers. So if I create a hidden layer, just a one layer fully connected from this many to 1,000 units, then I would have a matrix that would be 1,000 by 6 million. And then I'd have 1,000 bias terms. So I'd end up with 6 billion parameters just for the first layer. I already see the problem, how slow that is, how much data you would need to train 6 billion parameters. So we need to find some way to get the dimension of the data down, to gradually pull out the features we need as it goes through these layers. And so what we are going to use is convolutional neural networks, so CNNs they're called. And they're inspired by the audio engineers. So the audio engineers had a thing they called the finite impulse response filter, the FIR. And the idea is you would have a kernel like these three numbers, -1, 2, 1. You'd look at these three numbers in the input data. You would multiply each of them. So -1 times 3, 2 times 2, 1 times 4, just like that. You get 5. 5 would become the output. And then you would slide it forward. And you would multiply these against these numbers. And then that would become 7 and so on. And this is how you could do filtering, pull out different frequencies for audio. That's one-dimensional convolution. So given that we have this idea in 1 dimensions, what if we take it out into 2 dimensions? So now the kernel becomes a 2-dimensional matrix, but the same idea. So let's say we have an image. Let's assume for just a second that it's just one channel. So it's a black and white image, one channel. It's got a width and a height in pixels. We're gonna have some kernel. The kernel can be different sizes, but for this example, we're gonna do a 3 by 3 kernel. Okay? So what we'll do is we'll multiply 1 times 3 and add that to 2 times 2 and 0 times 4 and 0 times 2 and 3 times 0 and -1 times 1, just like that, until we get this number 6. And then that is going to become the upper left-hand corner of this. And then we're going to slide this whole window over by 1. And we'll do the same thing. We'll multiply this times that, and that times that, and that. We'll sum them all up, we'll get 18. And then once we've done the whole row, we'll start across doing the next row down. All right? Yep. Well, on this, it's a lot because I had to make the numbers big enough to fit on the screen. But of course, if this was a 1080 by 920 image, we're losing 1 pixel on each side is basically what this is.
But then aren't you not saving that much space then?
I haven't saved any space yet. Yeah. We're not saving much space at this point. But what we have done at this point is that instead of our first layer having 6 billion parameters, it has 9 parameters. Yeah, that's the big win right now, is because we're doing sort of shared weights across the whole image. So we have a lot fewer parameters at this point. Okay. So this is how we're going to do two-dimensional convolution. We're going to have these kernels. We're going to slide them across. There's also actually a bias term that you can add in here. So most of the two-dimensional convolutions is also a bias term as well. So instead of just 9 numbers, you would get 1 more number. Questions on convolution so far? The idea is that this kernel is going to be looking for certain features of those 9 pixels. Like maybe it's for looking at a diagonal where the upper right hand is light and the lower left hand is dark. And this kernel can go and sense that feature. Okay? Or maybe it means that the top half is lighter and the bottom half is darker. Those sorts of features. Now, if you're worried about losing the size a little bit, you can also zero pad it. So if you want to make sure that you have this original data here and you want the output to be the same size, you can add zeros all around, and then those get used in the process. And that way you get the same size matrix as you were originally inputting. Now, for 3 by 3, we only needed to add 1 pixel all around. But we could imagine a kernel that was 5 by 5. And if you did 5 by 5 and you wanted to keep the size the same, then you would do two layers of pixels around the outside. Does that make sense? Yeah. Yes. I'm sorry, real loud. Sometimes you don't want it to shrink. Sometimes you want to make sure that the size going in is the same as the size is going out. Yeah. Why are we doing convolution at all? Yeah. So what we're trying to do, let me slide a few slides forward and then we'll back up. All right. Okay, I can do it with this slide. We're going to end up with a whole bunch of kernels. And each of these kernels is going to be looking for a certain feature of the image. So maybe it's looking for a dot or a line or a shadow. We'll have a bunch of these and we'll slide them all over it. And the row of numbers that we get out, this thing, will actually represent how much of a white spotty thing is this, or how much of a white diagonal is this. And so we get sort of features rather than pixels, is the idea. Is that an okay answer? Okay. All right. So these convolutional layers, just like the fully connected layers, typically have an activation function after them. So when you get this, you then run it through a sigmoid function, or you run it through a ReLU, or some sort of nonlinearity. Because then you typically also do another round of these convolutions. The convolution kernels have a bias term. So besides these 9 numbers, there's 1 more that you can add and gets added to every single one of these boxes. A color image has 3 channels. So instead of a 5 by 5 kernel, you might have a 3 by 5 by 5. So besides it it will multiply the whole cube. It's in 3D, right? So maybe it's 5 by 5, that's the width and the height of the kernel, but it has a depth of 3. And so it can use all the different color channels while it's trying to identify these different features. And what features does it look for? We don't really know. It usually learns them as a part of backpropagation. And afterwards, you can kind of guess what it was looking for, but typically, we just let them learn whatever features they want. We seldom have a single kernel, right? A single kernel is looking for one particular feature. So we might have 7 or 8 features that we're looking for. So maybe we have an input, which is a 3-color 1080p image. And so the kernel has 3 in channels. And let's say we're looking for 12 different features to come out. We're looking for 12 different kinds of features for 5x5 with a bias, and it's a 0 padded. So then the output would be 12 channels deep, 1080 by 1920. So the number of parameters, though, is only 3 times 5 times 5 times 12, right? So 3 times 5 times 5 is the size of the kernel. But we have a dozen of them, so we have this many. And then we add 12 in for the bias terms, and you get 912 parameters. 912 parameters is way, 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 way better than 6 billion parameters. We have these weights. We're using the same weights all over the image. Yeah.
What are in channels and out channels referring to again?
So the in channels in the original image, the 3 in channels would be R, G, and B. In the 12 out, each one of those channels represents a different kind of a feature that particular kernel is looking for. So we're going to have 12 kernels. One kernel is going to be looking for red lines, let's say. Another one's going to be looking for blue regions. Those are going to be features. And so the output, each one of these channels is going to represent the different, the presence or absence of one of those features. Okay. So, questions so far? Yeah? No, not ensemble learning. This is convolutional neural nets. It's just keeping the number of parameters down for these really high number data. So not ensemble learning. Yeah? Did I do the multiplication wrong? 3 times 5 times 5 times 12. 3 in channels, 12 out channels, 5x5 kernels with the bias, so 1 for every one of the out channels, 0 padded, so it's the same size in and out.
Where's the plus 12 come from?
The bias terms. Yeah. Question? Thought I saw a hand go up. All right. All right. So this is convolutional neural nets. Nearly everything that takes an image or a video in starts off with several layers of convolutional neural nets. And that's what they're doing, is they're going through and they're looking for features. Now, we still have the problem of getting the size down. And there's a couple of different tricks that we use to get the size of the data down. And one is stride. So when we're doing this convolution, I was just showing you with a stride size of 1, which is, well, every time I do this, I move the box by 1. I can also say, well, let's do stride of 2, both in terms of rows and columns. So every time I do this 3 by 3 matrix, instead of just stepping 1, I'm going to step 2 forward and then work from there. And then I get a matrix that's half the size. Yeah? So that's a good way to get the size down a little bit. So the stride of the convolutional neural network is how much you move the kernel. And it works pretty nicely. Stride. Here is the formula for figuring out the output size. So you can do this for every direction. So maybe this is the input size is the number of pixels wide that an image is. The kernel size is the pixels, it's a 3 by 3K would be 3. The stride is the stride size, which by default would be 1. And then the padding is the rows of zeros that you added. So if you take the width and you subtract off the kernel size, and you add 2 times the padding, and you divide that by the number of strides, and then you add 1, that's how big the output is. This is this is one of those things that as you go through layers after layers after layers, starting with a reasonable shape and then working with these numbers so that this is always a whole number is a really good idea. If you have to, the frameworks will sometimes just they'll let you add, if you can always add more zeros. Anyway, this is just an important number to be able to compute. If I did this on a test, I would give you this formula. Yes? The stride is the amount that you're stepping this kernel along. So here, I did this kernel, multiplied it times these pieces, and then I moved 2 before I did it again. So that's the stride size of 2. So, yeah, no, it's fine. When you start off, you have a 2-dimensional thing. Here I'm doing stride size of 1. And then when I get to the end of this row, I would go down to the next row. Is that all right? So then the stride size, you can actually set it separately for each one. You can set the kernel to be non-square. But in reality, we almost always make the kernel square, and we always make the stride the same, both horizontally and vertically. Yeah. So this is 3 by 3. Oh, these numbers?
Yeah, if it's like 1.
Yeah, you do it for each dimension separately.
Yeah, okay, there we go.
Yeah. Other questions? All right. So yeah, go ahead. Over here. You start.
Okay. So are you looking at a lot of information to increase the stride?
Yeah. That's actually one of the goals. So what you're trying to do is sort of compress it down. So you say, I've got these features, that's what I really need, and I'm throwing away the details. And so yes, you're losing knowledge when you do this. You're shrinking it down, you're losing information, which is actually good. That's because at the end you want to have some fully connected network that actually does the logic of, oh, it's got these kind of ears and this kind of snout, it's probably a fox rather than a dog.
Okay.
All right?
And my second question is, with the stride, like the first layer, the number of parameters doesn't change. It stays the same, right? It's like the next layer, there's fewer inputs.
That's right. The input stays the same. It's just that the number of channels determines the depth of the tensor that's output. Is that the question?
Not exactly.
So again?
When we were comparing like 900 parameters to like 6 billion,
Yeah.
that 900 is like that first convolutional layer, right?
That's right.
But that won't change if you increase the stride. What will change will be like the second layers, number of parameters there. Right?
That's right. The size of the data coming out of the first layer changes, but the number of parameters doesn't change. That's right. Yes.
When we calculate the output size, why do we add like +1 at the end? And where does that come from?
You draw some pictures. You draw some pictures on a graph paper, and it'll become clear where the 1 comes from. Yeah. Over here. Yeah, there is a 1 here. If you have to draw it, just draw the picture out. You'll see why there's a 1 there. Yeah. Other questions? All right. There is a wonderful video on how this plays out as in backpropagation, how we compute the gradient of the weights in the kernel here. These things. We need to find a gradient for these so that they can learn and improve. So someone did a great video, and I'm going to just make you watch it. All right, so that's how convolution works. It's the same idea, though. It's very straightforward. It's differentiable, so we can find the gradient of the loss in terms of each of these weights, and then we can use that gradient to make the weights a little bit better at solving our problem. And so it's interesting, right, is that we have these ideas from calculus, the idea of derivative, and that's the whole thing that makes learning happen, is the gradient descent is decreasing the error, and that is how these systems learn, which is kind of cool, right? We still have a lot of data, and we'd like to shrink it down as we go through the layers, and one of the techniques that we use all the time in deep learning is the idea of max pooling. And with max pooling, we do this after the convolution, And so we have a matrix that represents the presence of some property, like a white blot. And so the ones around it tend to be similar. And so it turns out that it's really easy. If the white blot is there, one of the values in here is very high. So what we do is we just take the maximum and throw the other ones away. So here's the max pooling, 2 by 2 max pooling. I look at 2 by 2 matrix. I take the number that's the biggest there, and I copy that one across, and then I move to the next two. I take the biggest number, and I move that across. Take the biggest number, move it across. Max pooling, it's called. And once again, it's because this thing represents some features, the presence of some features. And so the really important question is it there at all? And by getting the maximum, we can say, yeah, that still indicates whether that feature is in that location. But we've gotten rid of 3/4 of our data, right? When you shrink it, the width down by half and the height down by half, you've gotten rid of 3/4 of your data, which is really a good thing. We're trying to get the size of the data down. Question on that? So this is something you'll see in a lot of image processing systems. Is you'll have a convolution layer, you'll have an activation layer, and you'll have max pooling. And you'll have another convolution layer, activation layer, max pooling. The question then becomes is the activation function and the max pooling, these are usually commutative. So we don't really care which one. And so it's actually more efficient to do the convolution and then the max pooling and then the activation function. But I've timed it on your average GPU and it really doesn't seem to speed things up very much. So the order doesn't matter. These two can go in any order. So this is kind of what things tend to look like in a lot of image recognition, image classification problems. So here I was trying to figure out which of 17 classes this is. So maybe one of the classes is dogs, one is babies with food in their mouth, one is chairs, one is cars. So I'm trying to get it down to these 17 numbers before it goes into the softmax. Yeah? But I start off with something big. This is 224 by 224 by 3. So the first thing I might do is run it through a convolutional 2D layer. And what I'm going for is it's starting out tall and wide and thin, right? There's only 3 channels. But the first thing I'll do is expand it out into 5 channels. It goes from 3 to 5. So I'm actually making it bigger. I'm making it fatter at this point. It's still the same width and height. It's a little bit fatter. But it's looking for some features. And then I'll run it through max pool to take it down to be half as tall and half as wide. So this is 1/4 the size. I'll run it through some sort of activation function like ReLU. And then I will do another convolution on it. And maybe now I'm going from 5 layers deep to 7 layers deep. Stays the same size. We'll see if I'm 0 padding at this one. I do a max pooling to take it down half as big. And then I run it through another activation layer. And now I have a reasonably sized set of numbers. At this point, I would flatten it out. So if I multiply 56 times 56 times 7, I should get 21,952. So I'm going to take it from this 3-dimensional tensor down into this 1-dimensional vector. That's flattening. And then that I can put into a fully connected layer. I can run it through a sigmoid. I can run it through another fully connected. And I'm getting smaller and smaller, gradually throwing away the extra information. And then I have 17, I run it through a softmax, and I get some 17 different probabilities for different categories. Yeah? This is a pretty common sort of thing, that you start off with something that's very wide, very tall, very skinny, and gradually you make it narrower and shorter and fatter. And in fact, some of them, they go all the way down to the point where it's just 1 pixel wide, 1 pixel tall, and 1,000 pixels deep. So they just keep doing convolutions all the way down until it's just one pixel wide, just super, super deep. Okay? Questions on that? Back there. The 3 to a 5. So I'm trying to find some features in here, in this picture. So maybe I'm looking for, curved areas of flesh color next with a dark background. So I need to have a reasonable number here of features that I'm extracting. And in this case, I'm going from 3 colors down to 5 different features. And then I'd use max pooling to make it narrower and shorter, which is that step here. Is that okay? Yeah. And then that is, these are gathered together to make even bigger, more features here. And once again, you kind of get fatter and shorter and narrower, gradually extracting out the important things necessary to recognize between these 17 groups. Yeah. Yeah.
So for when you expand it to 5 features, the first convolutional layer,
Uh-huh.
does that mean that you have 5 different kernels?
That's right, 5 different kernels. Yeah. And in this case, I'm doing 3 by 3 by 3 by 3 by 3, right? Because it's 3 by 3, and then there's the 3 colors. Yeah, and then I have 5 of those. Okay. So it's still a relatively small number of parameters, but I'm starting to extract the stuff I need from it. Yeah. Question back there? Nope, just hand wave around. Yeah.
How do you, like when we did k-nearest neighbors, we had like methods to optimize the hyperparameters. But here there's so many different things you can vary.
Yeah. So the question is with nearest neighbor, there were like 4 different parameters, hyperparameters. And now in neural nets, it's a huge number of hyperparameters. And how do we know what to do? And it's a great question, is how big should these convolutions be? And what is the good activation layer? And how many layers deep should it be? And how far should we go before we flatten it out? And the answer is it's one of those things that we're still figuring out. There is a thing called AutoML, which will automatically try tweaking all your parameters and get you something that converges well. But it's still sort of an art more than a science. Yeah. Okay. Question? All right. So I'm saying that, yeah. Yeah, so we start off with all of them with just random numbers. We fill the kernels with random numbers, and it's one of those things is the error propagates back from the loss, and it gradually figures out what's important. I'm sorry, real loud? Yeah. It's I don't want to say it's magic, it's calculus. It gradually, in that process of finding its way down that error surface, it optimizes all those parameters so that it can make this decision at the very end. And it's just the chain rule. I know it's weird, right? That it learns because of these things, but it will gradually figure out what those features it should be pulling out from, just based on the error that propagates up. Is that an okay answer? It's almost magic. Yeah. Okay. So as I said, this is a bit of an art, and you look at the size of the problem and the size of the image, and you gradually tweak it. So it's nice if we have a framework that lets us do these experiments very easily, where we can in one line describe how many outputs should come out of a hidden layer and what sort of activation function it could be and how we link them together. So there are lots and lots of neural network frameworks, which will save you from having to write all this stuff over and over again. For example, the convolution stuff that I just showed you in the video, I've never had to write that. I have always just used it from one of the frameworks. The one that you'll see a lot these days in a place like Georgia Tech is PyTorch. It's pretty standard in the research community. It's been a good standby for a long time. It came out of Facebook, and Lightning is sort of a nice wrapper for it. There's a lot of infrastructure for PyTorch, a lot of experience. The older one is TensorFlow. So TensorFlow was sort of the original open source neural network toolkit, came out of Google. And still, both of these are still used very heavily. In this class, we are using JAX, and their library that goes with it is called Flax NNX. That's their neural network library. And this is I think maybe the first undergraduate course in the world that's ever been used to use this particular technology for teaching, but it is the hot stuff right now. So everything at Google AI is moving to JAX and Flax NNX. 80% of the foundational models that are being created right now, the word on the street is they are all being done with JAX. So when we talk about Anthropic, their Claude stuff, DeepMind, Midjourney, so Character AI, XAI, Apple, they're all using JAX, and some of them are moving to Flax NNX in particular. And the reason why is because they're finding that they can train these networks much faster. So what the number on the street is twice as fast. They can train these neural nets twice as fast using JAX rather than PyTorch. So I thought it would be a good idea if I taught you the hot stuff now. I thought it would look great on your resume. And so I'm still learning it. I've been playing around with Flax NNX a little bit, and it is not surprising. If you have used all these other frameworks, Flax NNX is very, very similar. And I'm just going to give you a couple of samples of code to do this. Okay? All right. And actually, let me just mention, I've been emailing back and forth with the Flax NNX team at Google, and they are very excited that all of you are learning it. So send your resumes. The JAX ecosystem is a big thing. So here we can think of it as a stack, right? You got your hardware, and it works with a CPU or a GPU or a TPU. So the back end, the XLA, Accelerated Linear Algebra library, that is optimized for all of them. So if you take this model and you train it on the Google network using the TPUs, it will do the right thing for you, which is great. And if you move it to a GPU, it'll do the right thing. And if you have to do it on a CPU, it'll do the right thing. The XLA library, this is all C++. Built on top of that was JAX. You've been using JAX. But JAX is just like NumPy, but it adds in this auto differentiation and some vectorization and the just-in-time compiler, which makes it more efficient. It's also a little bit more of a functional programming paradigm. So we do a lot of things without side effects. And in fact, the just-in-time compiler sort of counts on that. If you do a lot of side effects, the just-in-time compiler won't let you do it. Built on top of that is Flax NNX and Optax. So one of the things they did that was very interesting is they separated the idea of creating a model for neural nets. So the idea of the fully connected layer and the activation layers, those are all under Flax NNX. And then the process by which it does the optimization, so taking the gradients and applying them to the weights, that is all under this Optax library. So when you're working in Flax NNX, you're typically using both of them at the same time. There are a bunch of other little frameworks that you use. There's Orbax, which does checkpointing. There's Chex, CHEX, like Chex Mix. And that's for testing different things. There's a whole bunch of different frameworks. But these are the two that you're going to be working with the most. Questions on that? All of this is open source. You can go on the website. It's on GitHub. There is also a library of models that are pre-trained. So one of the things that's cool about PyTorch is that when you go on the Hugging Face website, do you guys know about Hugging Face? There's a bunch of standard models. So there's a bunch of open source models. You can download them and use them. And one of the things that's annoying is that the Hugging Face ones don't really work nicely with the JAX framework. So Google is doing their own Hugging Face type repository. It's called Bonsai. And so you can get a lot of the open source pre-trained models from Bonsai. So for example, they did a bunch of large language models called Gemma when they were making Gemini. And so you can get the Gemma models for free. So that's the Bonsai library. Here's what it looks like when you create a model. And so this is your homework assignment, actually. You have to write it without Flax. But if you're doing MNIST and you have to have a fully connected layer with 784 inputs and 128 outputs, this is how you would create that in Flax. So I'm creating a big model. In the init method, I'm creating the different layers. With each one that uses a random number generator, you have to pass that in. So whenever we're creating this, we pass the number generator in, the random number generator in. the functions like ReLU, you just pass in the function and that's the whole thing. And then at the end here, I have a softmax. Then in the calling of this model, you are making the prediction. So you say X is the output of the fully connected layer, and then you feed that into the activation layer, and then you feed that into the second fully connected layer, and then you feed that into the softmax. The miracle of auto differentiation is as soon as you just define the call, it can automatically figure out how to compute all the gradients from there. And so it can update the weights for you, which is really cool. Okay. So this is how you describe your model. Yeah? Questions on that? Once you've defined your model, if you want to train it, this is how you would do it. So here I created the model instance. I passed it a new random number generator seeded with 0. I created an optimizer. I passed it in my model, and I said, you're going to be updating all the parameters. And then I passed in the Atom W optimizer. So Optax has a nice thing that does, it's a little bit smarter than just boring gradient descent. It's called Atom. It works beautifully. But you pass it a learning rate and a momentum, and we've created the optimizer there. Then you define your loss function. So here I said, for this model, I'm going to have this input and these labels. So I will run them through the model. The model, to do a prediction, you just pass in the inputs as a tensor, and you get out the softmax output. So I'm sorry, here. The softmax output here, that's where it gets returned, right there. Then we can compute the loss. So we can ask Optax to do a softmax cross entropy loss with integer labels. So this is just a list of integers. This is numbers between 0 and 1. And it is doing the cross entropy loss, taking the mean of that, and you get this number. Once again, the cool thing about auto differentiation is that this already has all the stuff you need in order to do the backpropagation on it. So we can just ask it, NNX, create a function that's going to return the gradients of this loss function at any given point. So this is where the auto differentiation happens. You take this function and you say, give me something that gives the gradients for it. And then you have a loop where you actually go through the data. So here I'm going through a bunch of epochs. I'm going through a bunch of batches. So here's the batch X. These are the input. These are the labels. I use this function that I just created here, this one. And I feed the data and I say, here's the model. Here's the X. Here's the labels. Give me the loss and the gradients. And then I pass those gradients into the optimizer. I say, update this model using these gradients. It uses the Atom algorithm for me and updates the model. And then I go through the loop again. And then when I'm all done and I want to save them, I ask for the state of the model. And then I can just write the weights out in a pickle file. You guys, have we done pickle files already? We have, right? I think we used them. So it's just a binary representation of Python data. It's pretty slick, right? That's not a lot of code. When you have to write this and you have to do all the differentiation and stuff starting on Sunday, right? You start on Sunday. Yes, on Sunday, you'll see that involves a lot more code than this. They took care of all the boring stuff for you. Questions on that? When you want to produce, so what do we got here? We've got create the model. We've got prepare to train. We've got the training loop and saving the weights out. When you want to do some predictions with it, you create a model again, you read in the weights, and you set the state on the model. And now you can run the test data through it. You get a bunch of soft predictions. And then you take the argmax for each row, and that will get you a hard prediction. Yeah?
So like in the previous code, we can see like there's like a convolutional like network. Like it's like 128.
That's a hidden layer. So this is a fully connected layer. These are linear. There's no convolutional neural nets here.
But it's like predicts like one number.
Yeah, I figured it.
Is that 10 feature like making you sure?
Yeah, that's why this is 10, because the output has to be one of 10 different digits. Yeah. Yeah, so this is an input of 784. It goes down to 128 numbers, and then it goes from 128 to 10. Yeah. So yeah.
Can you go back a few slides?
Uh-huh.
So where you calculate the loss, what is the log?
Logits, this is the soft predictions. So the same as this thing. You put the data in, you get a matrix of predictions. So you get a row for every input, and then you get a column for every possible category that comes out, and you get a number between 0 and 1 for each one. They add up to be 1 in each row. Okay. It is, if you have a GPU and a TPU and a CPU in your computer, you might want to be very specific about what device your tensors are living on. So when you create a JAX array, one of the parameters you can pass is the device. And here I'm saying, put this, make this array on my first GPU. So how did I get the list of GPUs? I said, JAX, give me a list of all the GPUs that you can see on this system. And then, you should check to make sure you've got at least one. But here I'm saying, and then just put this array on the first one. And so when you want things to run really fast, right, you put them on your GPU and you put them all on your GPU. So if you're going to multiply two arrays together, you want to make sure they're both on the GPU. Yeah.
That means by default, JAX.
I don't know. I'm sorry. You're going to be, so all of you should know that you have, because you're in this class, you have access to the PACE system. And so as we're doing bigger and bigger machine learning stuff, you're going to actually be able to do it on PACE instead of on your laptop. And so one of the things that we're figuring out is how to make it run fastest on PACE, regardless of the devices. And so I hope to have a really good answer for you in the next week. But I don't have a good answer right now, what the default is. Other questions? Ones I can answer? All right. As you read the documentation for Flax and NNX, you're going to keep running into this word pie trees. And so what happens, right, is you get all these gradients. Well, there's a gradient for this weight matrix, and there's a group of matrix of gradients for this weights matrix, and a matrix of gradients for this weights matrix. You've got gradients for a vector of gradients for this bias part, and this bias part, and this bias part. You need to make sure they all go to the right place. So it turned out that this data structure they needed over and over again. And so they created the pie tree. And so it's a nested structure. It's got things that are dictionaries, list, and tuples. And then out of the leaves, there's typically either a number or there is a JAX array. And so they use these over and over again. The JAX and Flax community loves pie trees. So all the parameters, the weights that are in your model, those are all going to be pie trees. The gradients, when you compute them, they're all pie trees. The modules, you can pull out the modules as pie trees. All the data sets that you train on, you can actually, it does a good job of interpreting those. You can have the input and the output inside a pie tree, and it does the right thing. So you're going to bump into pie trees again and again and again. That's all they are. It's just a combination of lists, dictionaries, and tuples. And the leaves are typically these JAX vectors, JAX tensors. Okay. Not that heavy. I just want you to know what's going on. Questions? So now we started off with the philosophy of neural nets. We did linear regression and logistic regression and the loss function and gradient descent. We started off with the real simple stuff, and now we're getting to more and more sophisticated techniques that the deep learning community uses. And we're going to continue on that journey for a couple of more weeks. So thank you so much, and I will see you on Tuesday.